So we've discussed the Laplace transform from its definition, and we've computed the Laplace transform of some functions using its definition. We also discussed a very important theorem regarding the linearity of the Laplace transform. The Laplace transform is a linear transform, and this allowed us to compute other Laplace transforms much quicker. And here we'll expand and discuss some theorems, in particular an existence theorem. We want to know when are we guaranteed a Laplace transform. And so before we get into that, we're going to need some definitions. The first one being piecewise continuous. A function f is piecewise continuous on this interval if in any t between a and b, or with these bounds, there are at most a finite number of points, tk, where tk minus 1 is strictly less than tk, because just the ordering of the k's there, at which f has finite discontinuities and is continuous on each open interval from tk minus 1 to tk. Okay? So that's called piecewise continuous. It's important here that you have a finite number of discontinuities that are finite discontinuities. Okay, so it's not diverging. Okay, so how a function would look, is something like, say, go up to here, say this is t1, and we get some discontinuity. This goes down, and say maybe you get another discontinuity, and on. Okay, like say t2. So here we drew two discontinuities, and they are finite discontinuities. Okay, it's not like 1 over x near x equals 0. That's not a finite discontinuity because you have an asymptote there. Okay, so you have a divergence there. Okay, so that's what piecewise continuous is. What about exponential order? Okay, a function f defined on the interval is said to be of exponential order as t goes to infinity if there exist constants c and m, both positive, and t, also positive, such that the function, the magnitude of the function, right, absolute value of the function, is less than or equal to this m and e to the ct for all t strictly greater than t. So let's decipher this, okay? Sounds kind of complicated, but it's really not. This t strictly greater than capital T is just telling you that eventually, so the function could wiggle or behave weird up until some finite value of t, and then beyond that, the asymptotic values is what's important. So what happens as t goes to infinity is what's important. So that's what that's telling you. It's telling you, well, you could kind of ignore everything before some finite value of t. And this m and c, m is just a constant that you could multiply an exponential function with, and c is just telling you the rate that this exponential function is growing. But what's important is that you can find some c or m. So just there exists. It doesn't have to be, there aren't really constraints on c and m except that they're positive. Okay? So as long as you could write f as less than or equal to some constant times this, then we say it's of exponential order. And that just basically means that you could bound the function by an exponential function. Okay? So if you could bound the exponential by an exponential function at very large values of t, as t approaches infinity, then the function is of exponential order. So let's look at some examples. T to the power n is of exponential order. You could see that by taking the limit of the ratio of tn over some e to the power ct, and this will always go to 0 as t goes to infinity. Okay? And we take that ratio because we want to see if we could have, this less than e to the ct. So if you divide both this inequality by e to the ct, you would get something like this. And we want to make sure that that stays less than or equal to some m, okay? And we're concerned with as t goes to infinity, so here, what you would do is use L'Hopital's rule to eventually show that this goes to 0. What about an exponential function? That's obviously of exponential order, okay? If you look at this ratio there, you see that for c greater than or equal to a, you're going to get that this term goes to, is going to be bounded, right? If c equals a, then you get that this ratio is 1, which is less than or equal to some m, or, m could be taken as 1. If c is greater than a, this will be negative, and as t goes to infinity, this goes to 0, so it would be less than some constant. And notice the only restriction on c here is greater than or equal to a. And that's no big deal, because all we need to show is that there just exists, okay, just one, at least one, c or m where this is true. And we could definitely choose a c that's greater than or equal to a for whatever a is in that function. E to the t squared is not exponential order. If you take a look at this ratio, you get this, and this always goes to infinity, regardless of the c that you choose. Okay, so no matter what c you choose, as t goes to infinity, this is going to be positive, that's going positive, and this is going to go to infinity. What about this? Well, 2 cosine t is actually bounded by 2. And we could just choose c equals 1, because why not? And we get that 2 cosine t is less than or equal to this, okay? And we didn't have to choose like c equals 1. We could choose pretty much any positive c there and get the result. But, this is just for illustrative. All we need to find is 1 again. Okay, so here goes another important theorem besides linearity. Sufficient conditions for the existence of the Laplace transform. If a function f is piecewise continuous on this interval and of exponential order with c such that we see here, then the Laplace transform of f exists. Okay, so that integral of the Laplace transform in the definition converges for s strictly greater than c, okay, where c is chosen to bound this f, okay. So that's sufficient conditions, right? That's not necessary conditions. Okay, so we just know that if we have piecewise continuity and exponential order, then the Laplace transform will converge for a suitably chosen c, s greater than c. Does that mean that if your function is not piecewise continuous or not exponential order, that the Laplace will diverge? No. Okay, these are sufficient but not necessary conditions. So piecewise continuity and exponential order are sufficient conditions for Laplace transform, but not necessary. Some quick examples: t to the minus 1/2 is not piecewise continuous, because at t equals 0 you get a divergence, okay, to plus infinity. But the Laplace transform of it exists, okay? And this here is not of exponential order, but the Laplace transform also exists. So, these are sufficient. You're guaranteed that if you have a piecewise continuous function of exponential order, that you'll get the Laplace transform converging, but they're not necessary. In other words, there are functions that aren't like that, but they do have a Laplace transform. So let's look at an example. Consider the function that you see here. Okay, so 0 from 0 to 3, and then right at 3 it jumps to 2, so we get a jump discontinuity there. The Laplace transform of this, how do you take that integral? Well, you just integrate based on the piecewise nature of this function. So from 0 to 3, we have one value at 0. Then 3 to infinity, we have this other value of the function there. This one is 0. Over here we integrate and we get this value here. Okay. Be careful not to think you could use a Laplace transform of 1 in a trivial way, because this is integrating from 3 to infinity, not 0 to infinity. Okay. So this is not the Laplace transform of 2, for example. And so we get this, and for s is greater than 0. So we've looked now at many examples, and we constantly stating where s is valid, where this would converge. So if s was 0 or negative there, you would get divergence. In the future, we'll refrain from talking about the domain S where it's valid, just when it's obvious. Okay, so it's clear after all of these examples. Just a note there. All right, here goes another theorem. So the behavior of f of s as s goes to infinity. If a function f is piecewise continuous and of exponential order with c such that we have this, in the Laplace transform, then we know from the existence theorem that the Laplace transform exists, and is this equal to f of s, then the limit of f of s goes to infinity is 0. So if you go back and look at all the Laplace transform we've looked at so far, they're all piecewise continuous and of exponential order, except in that remark, right? But otherwise, you could tell that as s goes to infinity, you get a 0. So this was the case here, and it was the case for other Laplace transform we've looked at before. This goes to 0, goes to 0, goes to 0, and on and on. Okay, so we looked at many Laplace transforms, and they all go to 0, and that's not a coincidence. This theorem is telling you that that's how they should behave. Having said that, there are Laplace transforms that do not have this property, which implies that the transformed functions were not piecewise continuous or of exponential order, and that's fine. So just to kind of take a quick example here, so if you have f of s is equal to 1, okay, so that the Laplace, so that the transformed function would give you a Laplace transform equal to 1. Well, actually, this is the Dirac delta. If you take the Laplace transform of the Dirac delta function, you get 1 there, okay? And of course, some people would object to calling the Dirac delta function a function, okay, rather than a distribution. But let's not get too technical for our purposes here. The point is, if you do find, a Laplace transform function that doesn't respect this property, that's okay. It just means it wasn't piecewise continuous or of exponential order. There are other types of functions. And just kind of a quick note here that this change of scale theorem could be helpful. So if we have this Laplace transform and a strictly greater than 0 is a constant, then the Laplace transform of f at is equal to 1 over a f, capital F now, the Laplace transform of lowercase f, s over a. Okay, so wherever you see a s, you would plug s over a, and you'd multiply that by 1 over a, and you would get the Laplace transform of the function with at, okay, plugged in. So instead of t, where we see a t, you plug in an at. Okay, just change of scale theorem there could be helpful.